Hello students, hope you're doing well. In this video, we'll look into the next topics under the topic magnetism and matter. The topics that we're going to see is properties of magnetic material. So in this, we'll see what are the various properties of a magnetic material, various terms that are associated with it, and then what are the relations between all those terms. First, let's define intensity of magnetization. Intensity of magnetization is defined as magnetic moment developed per unit volume in a specimen or a material when subjected to uniform magnetizing field. So what does intensity of magnetization tell us? It tells us how much magnetization has been induced in the material when the material is placed in external magnetic field. So this is represented by I. So this is given by I equal to magnetic moment per unit volume. So where M is magnetic dipole moment induced, and V is volume. Now we know that magnetic dipole moment can be written as pole strength into length of the magnet, that is magnetic length of the magnet, and volume is area of cross section into length. So that would imply I equal to M into L by A into L. If I strike off these two things, I'll be left with M by A. So I can say intensity of magnetization is equal to magnetic pole strength induced per unit cross section area. So this is magnetic pole strength induced per unit cross section area, right? So we can define intensity of magnetization either by this or by this. Then we have magnetic intensity, or also known as magnetizing force. So how do we define it? In a vacuum at a point, magnetic induction is B naught, then magnetic intensity there is given by B naught by mu naught. So H equal to B naught by mu naught gives the effect of magnetizing force, or magnetic intensity is what? The net effect of magnetic field present at any point. So if it is not vacuum, if it is some other material, then I can add H equal to B naught by mu, where mu is the absolute permeability of that particular material. So magnetic intensity gives us what is the effect of magnetizing force or magnetic field present in that particular position. Then we have magnetic susceptibility. As the name suggests, susceptibility tells us about the measure of how susceptible a material is to get magnetized. So the magnetic susceptibility of a material is the ratio of intensity of magnetization to the magnetic intensity. Now this magnetic intensity is the applied field and this I is the induced field. So susceptibility is induced field produced per unit applied field. So this can be further written as, if I multiply and divide by mu naught into I is induced magnetic field and mu naught into H is applied field. So in this way, a material with greater susceptibility will be easily magnetized, and a material with lower susceptibility cannot be easily magnetized. Then we have magnetic permeability. Now what is magnetic permeability? As we have seen, if I know what is magnetic intensity, then the ratio of magnetic field at that point by magnetic intensity would give us magnetic permeability. So magnetic permeability mu is given by B by H. So this is absolute permeability of that particular medium. Then we have relative permeability. Relative permeability is the ratio of permeability of material to the permeability of free space. So mu, which is absolute permeability of material, mu naught, which is permeability of free space. So relative permeability is ratio of them. So it's a dimensionless quantity. Then we have magnetic induction. So magnetic induction talks about the net magnetic field inside a magnetic material when placed in an external magnetic field. So let's say I have a magnetic material something like this, and I have a magnetic field which is applied magnetic field in this direction. So let the applied magnetic field be B naught and induced magnetic field be Bi. Then I can say the net magnetic induction B equal to Bi plus B naught. So Bi is what? Induced magnetic field. Now Bi can be written as mu naught into I. I is intensity of magnetization, and B naught can be written as mu naught into H, where H is magnetic intensity. From these two things I can get B equal to mu naught into I plus mu naught into H. Or I can write B equal to, I'll take out mu naught into H outside, I'll be left with 1 plus I by H. Now we have seen that I by H equal to chi. This is what? This is susceptibility. So I by H equal to chi is susceptibility. So we can write B equal to mu naught into H into 1 plus chi. So this is magnetic field intensity, magnetic intensity and magnetic susceptibilities relation. So the relation that we got is B equal to mu naught H into 1 plus chi. This is the relation we got. Now 1 plus chi equal to mu r. What is mu r? Relative permeability. So mu r is relative permeability. So that would imply B equal to mu r into mu naught into H. So B equal to, I can write it as mu m into H, where mu m equal to mu r into mu naught, or you simply mu or mu m. Some books use mu m and some books use only mu, is what this is called absolute permeability of the medium. This is absolute permeability of this medium. So these are the relations, different relations we have. So I can write net magnetic induction equal to absolute permeability of medium into H. H is magnetic intensity. And this is how we have, if you remember, we have defined mu, permeability of a medium or absolute, which is equal to P by H. After this, let's look at how induced magnetic field varies with change in applied field. Now this loop is called magnetic hysteresis. Now hysteresis is a feeling of being left behind. So here what we see is the induced magnetic field always trails the applied field. That's why we call this loop as magnetic hysteresis. Now let's see what is happening. Now let's say I start, I take a magnetic material and start slowly increasing the applied field H. So here B, instead of P we have taken I. Now when I slowly increase, what will happen? The magnetic field increases. The magnetic field increases to a maximum value, and then there is no more increase because all the magnetic domains which are there, which are present, or magnetic atoms which are present, have already aligned. That means magnetic saturation has reached. Now what I do, I start decreasing this applied magnetic field. Now when the applied magnetic field becomes zero, I still see that there is induced magnetic field retained in the material. That induced magnetic field, here you can see, retained in the material is called retentivity. So if I have to define retentivity, how can I define retentivity? Retentivity is induced field retained by the material. Retained by the material when applied field is made zero. Induced field retained by the material when applied field is made zero. Now if I further go on decreasing magnetic field and apply the applied field in opposite direction, at some point you can see that at this point the induced field becomes zero. So this point is called coercivity. So this we call it as coercivity. It's written there, but it's very small letters. So coercivity, how can I define coercivity? Coercivity is the amount of applied field in opposite direction. Amount of applied field in opposite direction to make the induced field zero. This is called coercivity, right? Now, why this loop is so important? Just by looking at the shape of the loop, I can, find out whether a material is having high retentivity or low retentivity or high coercivity or low coercivity. Now, depending on these values of retentivity and coercivity, I can choose the material for any specific purpose. For example, I want to make a permanent magnet. Now, permanent magnet is a magnet which retains magnetism even after the field is taken out. So it should have high retentivity. Similarly, it should not be easily demagnetized, or its magnetism should not become zero easily. So it should have high coercivity. So if the shape is something very thick, something like this, maybe something like this, that material is suitable for permanent magnet. Similarly, if I want to make an electromagnet, now electromagnet is something which has magnetism only till the applied field is there, right? When the applied field is made zero, the magnetism should also become zero. That means its retentivity as well as coercivity should be small. So in that case, maybe the graph would be something like this, very thin. So by looking at the plots or magnetic hysteresis curves, I can identify directly whether a material is suitable for a specific purpose or not. So this is what is there in properties of magnetic materials. What all things we have seen? We have seen various you know terms like magnetic intensity, intensity of magnetization, magnetic susceptibility, permeability, relative permeability, magnetic induction, and try to define them. And then we found a relation between them, how they are connected to each other. And after that, we have seen the variation of induced magnetic field with applied field, and we call that as magnetic. Of course, it's called as magnetic hysteresis loop. And by looking at the loop, how we can identify whether that material is suitable for a specific purpose or not. Hope you could follow everything that we have discussed in this. Thanks a lot for watching this video, and keep watching other videos of Get My Class. Thank you very much once again.